Welcome to our deep dive into Google Cloud Platform's hybrid connectivity solutions. Today we're going to explore how modern enterprises bridge their on-premises infrastructure with Google Cloud to create seamless, secure, and high-performance hybrid environments. In today's enterprise landscape, the question isn't whether to move to the cloud, but how to do it strategically. Most organizations operate in a hybrid world where cloud infrastructure extends rather than replaces existing data centers. This creates unique networking challenges that we'll solve together. We'll cover two main connectivity options: Cloud VPN for encrypted connections over the Internet, and Cloud Interconnect for dedicated private fiber connections. But connectivity is just the foundation. We'll also explore the critical challenge of accessing Google APIs privately from your on-premises environment. The diagram you'll see shows the fundamental hybrid architecture pattern that every enterprise needs to understand. Notice how we have three main components: your enterprise data center with existing applications and users, Google Cloud Platform with its services, and the connectivity layer that brings them together. Let me walk you through the fundamental decision every enterprise faces. Should you use Cloud VPN or Cloud Interconnect? This isn't just a technical decision. It impacts your budget, timeline, security posture, and long-term scalability. Cloud VPN creates encrypted IPsec tunnels over the public internet. It's quick to set up, cost-effective, and provides good security through encryption. However, performance depends on internet quality, and you're limited to about 3 gigabits per second per tunnel. Cloud Interconnect, on the other hand, gives you a dedicated fiber connection directly to Google's network. This means consistent latency, higher bandwidth options, 10 or 100 gigabits per second, and traffic that never touches the public internet. The trade-off? Higher cost and longer setup time due to physical fiber installation. Partner Interconnect sits in the middle. You get the benefits of a dedicated connection but share it with other customers through a service provider. This reduces cost and setup complexity while still providing better performance than VPN. The key insight here is that both options require cloud routers and BGP for dynamic routing. Never use static routes in production. You'll regret it when you need to scale or handle failover scenarios. Cloud Interconnect Architecture Deep Dive. Now let's dive deep into how dedicated interconnect actually works. This diagram shows the complete data path from your on-premises router all the way to your VPC networks in Google Cloud. Starting from the left, you have your customer router in your data center. This router needs to support BGP and should have its own autonomous system number ASN. In our example, we're using ASN 65001. Which is in the private ASN range. The physical connection goes to a Google Edge router at a colocation facility. Google operates edge locations in major metropolitan areas worldwide. The connection between your router and Google's Edge router is a Layer 2 circuit. It's like having a very long Ethernet cable. Here's where it gets interesting. You can create multiple VLAN attachments over a single physical interconnect. Each VLAN attachment connects to a different cloud router, allowing you to segment traffic or connect to different VPC networks. Think of it like having multiple virtual connections over one physical wire. The cloud router is a regional resource that handles BGP peering and route advertisement. It's the brain that learns your on-premises routes and advertises your VPC subnets back to your network. This creates dynamic, automatic routing that adapts to changes in your network topology, creating dedicated interconnect, step by step. Let's walk through the actual G-Cloud commands to set up a dedicated interconnect. I'll explain every parameter so you understand exactly what each command does and why. The first command creates the physical interconnect connection. The customer name parameter is what appears on Google's provisioning systems. Make sure it matches your official company name. The interconnect type must be dedicated for this scenario. The link type specifies the physical interface type. Link type Ethernet 10G base LR means you're requesting a 10 gigabit Ethernet connection using long-range optics. This determines what type of optical transceiver you'll need in your router. The location parameter is crucial. This must match an actual Google colocation facility where you can install your equipment or cross-connect to your provider. Each location has a specific code like LAX Zone 1770 for Los Angeles. The requested link count is typically 1 for most deployments, but you can request multiple links for higher bandwidth or redundancy. Remember, each link requires separate optical transceivers and potentially different physical routers. After creation, you'll receive a letter of authorization, LOACFA, that you'll need to provide to the colocation facility. This document authorizes the facility to connect your equipment to Google's equipment. Cloud router configuration. The cloud router is absolutely critical to your interconnect setup. Let me explain each parameter in detail, as getting this wrong can cause routing issues that are painful to debug. First, we specify the VPC network this router will serve. The router can only advertise routes for subnets in this specific VPC network. If you have multiple VPCs, you'll need separate routers or VPC peering. The region parameter determines where the router runs and which interconnect locations it can connect to. Choose a region close to your interconnect location for optimal performance. The ASN is crucial for BGP. Use an ASN from the private range, unless you have a public ASN. This ASN will appear in BGP advertisements and must be unique in your routing domain. The advertisement mode determines how the router shares routes. Default mode automatically advertises all subnet routes in the VPC. Custom mode gives you granular control over which routes to advertise. Use this for complex routing scenarios or security requirements. When you enable global dynamic routing, this router can learn and advertise routes for subnets in all regions of this VPC, not just the local region. This is essential for multi-region deployments but can create complex routing tables. VLAN attachment and BGP configuration. Now we're getting to the heart of the interconnect setup. The VLAN attachment is what actually carries your traffic, and the BGP peer configuration is what makes the routing work. When creating the VLAN attachment, the VLAN parameter specifies which VLAN tag to use on the physical circuit. This must be coordinated with your network team. Whatever VLAN you specify here must be configured on your on-premises router as well. The router parameter links this attachment to the cloud router we created earlier. This establishes the relationship between the physical connection and the routing logic. For the BGP peer configuration, the peer IP address is critical. This is typically a linked local address, 169.254.x.x, that serves as the next hop for your on-premises routes. Google will provide the specific IP range to use. The peer ASN must match the ASN configured on your on-premises router. If these don't match, the BGP session will never establish, and you'll have no connectivity. The advertisement mode here determines what routes this specific peer will receive. Default sends all subnet routes, while custom, with set advertisement ranges, lets you control exactly which networks your on-premises side can reach. Always verify the BGP session is established after configuration. A down BGP session means no traffic flow, even if the physical connection is working perfectly. HAVPN Architecture Overview. Now let's shift to Cloud VPN, specifically HAVPN, which is Google's recommended solution for production workloads. The architecture shown here demonstrates why HAVPN achieves 99.99% availability. The key to understanding HAVPN is the 4-tunnel design. You have 2 on-premises gateways, for redundancy, and 1 HAVPN gateway with 2 interfaces, in different zones. This creates a full mesh of tunnels. Each on-premises gateway connects to both HAVPN interfaces. Why 4 tunnels? Because this design eliminates all single points of failure. If one on-premises gateway fails, traffic flows through the other. If one Google zone has issues, traffic uses the other interface. If a single tunnel fails, 3 others remain available. The IP addresses shown, 35.242.x.x, are automatically assigned by Google when you create the HAVPN gateway. These are the destination IPs your on-premises VPN devices will connect to. Notice that all tunnels terminate on a single cloud router. This router manages BGP sessions for all tunnels and handles failover automatically. When a tunnel goes down, BGP withdraws routes through that path, and traffic immediately switches to healthy tunnels. The link local addresses, 169.254.x.x, are used for BGP peering between your routers and the cloud router. Each tunnel gets its own /30 subnet for this purpose. Creating an HAVPN gateway is simpler than interconnect because there is no physical provisioning involved. However, the configuration details matter enormously for security and reliability. The network parameter specifies which VPC this gateway serves. Like Cloud Router, the VPN gateway is tied to a specific VPC and can only route traffic for that network. The region determines where the gateway runs and affects latency to your on-premises locations. Choose the region closest to your primary data center for optimal performance. When you create an HAVPN gateway, Google automatically provisions 2 external IP addresses in different zones within the region. This is different from classic VPN, which only had one IP address and couldn't achieve 99.99% SLA. The describe command shows you these IP addresses, which you will need to configure on your on-premises VPN devices. Save these IPs immediately. You will reference them multiple times during setup. The cloud router creation is similar to the interconnect scenario, but for VPN, you typically use BGP over the tunnel interfaces rather than dedicated interconnect attachments. External VPN gateway and tunnel creation. This is where HAVPN setup becomes more complex than simple point-to-point VPN. We need to define your on-premises infrastructure to Google Cloud so it can establish the proper tunnel relationships. The external VPN gateway definition tells Google about your on-premises VPN infrastructure. The interfaces parameter maps to your actual on-premises public IP addresses. Interface 0 and Interface 1 represent your 2 on-premises VPN gateways. These IP addresses must be public, static, and reachable from Google's network. If you are behind NAT or using dynamic IPEES, HAVPN won't work reliably. Now for the tunnel creation. This is where the magic happens. We are creating 4 tunnels to achieve full redundancy. Let me explain the tunnel naming and connection pattern. Tunnel 1 connects HAVPN interface 0 to your on-premises interface 0. Tunnel 2 connects HAVPN interface 1 to your on-premises interface 1. These are the straight connections. Tunnels 3 and 4 are the cross connections. HAVPN interface 0 to on-premises interface 1, and HAVPN interface 1 to on-premises interface 0. This cross-connection pattern is what eliminates single points of failure. Each tunnel gets its own shared secret, pre-shared key. Never reuse shared secrets between tunnels. This is a security best practice and helps with troubleshooting if one tunnel has authentication issues. The IKE version should always be 2 for better security and performance. IKE v1 is legacy and has known vulnerabilities. BGP interface and peer configuration. This final step is where we configure the routing intelligence that makes HAVPN truly dynamic and resilient. Each tunnel needs its own BGP session, which means 4 router interfaces and 4 BGP peers. For each router interface, we specify a unique IP address in the 169.254.x.x range. The /30 mask gives us exactly 2 usable addresses per tunnel, one for the Google side and one for your on-premises side. The I-address parameter is the Google Cloud side of the BGP session. Your on-premises router will peer with this address. The corresponding peer-I-address in the BGP peer configuration is your on-premises router's address. Why 4 separate BGP sessions instead of 1? Because each tunnel can have different characteristics: latency, bandwidth, cost. BGP can use these attributes to make intelligent routing decisions and provide fast failover when tunnels go down. The peer-ASN must match across all BGP peers since they represent the same on-premises network, but they're coming from different tunnels. This tells BGP that these are multiple paths to the same destination. Each BGP peer can advertise the same routes, creating multiple paths. BGP will automatically prefer the best path based on various attributes, and if that path fails, it immediately switches to the next best path. The key to HAVPN success is that when a tunnel fails, the BGP session over that tunnel fails too, immediately removing those routes from the routing table. Traffic switches to healthy tunnels typically within seconds. Always monitor BGP session status after configuration. 4 established BGP sessions mean full redundancy. 3 or fewer sessions mean you have a potential single point of failure that needs investigation. Now that we have established connectivity between your on-premises network and Google Cloud VPCs, we face a critical challenge that many architects overlook. How do your on-premises applications access Google APIs like Cloud Storage, BigQuery, and Pub/Sub? By default, Google APIs are accessible via public endpoints with addresses like storage.googleapis.com resolving to public IPs in the 142.250.x.x range. This creates a problem for most enterprises because their security policies typically prohibit internal servers from accessing the public internet. Think about this scenario. You have spent weeks setting up a beautiful private connection between your data center and Google Cloud, but your on-premises application servers still cannot reach cloud storage because your firewall blocks public internet access. This is where private access patterns become essential. The diagram shows this challenge clearly. Your application server needs to reach storage.googleapis.com, but your corporate firewall blocks the public route. We need to redirect this traffic through your private connection instead. Most enterprises have policies requiring that all traffic to Google Cloud must use private connectivity, sensitive data never traverse public networks, and internal servers cannot access the public internet. These policies create the need for sophisticated private access patterns. We have 2 main solutions. Private Google Access for on-premises, which redirects API traffic through your private connection, and Private Service Connect, which creates dedicated endpoints in your VPC. Let us explore both approaches in detail. Private Google Access Architecture. Private Google Access for on-premises is a clever solution that redirects API requests from your data center through your private connection instead of the public internet. The magic happens through DNS resolution and BGP route advertisement. Let me walk you through the complete data flow. First, your on-premises server makes a DNS query for storage.googleapis.com. Instead of returning the public IP address, your corporate DNS server returns a private IP address in the 199.36.153.8/30 range. This is the key insight. Google operates private endpoints at these special IP ranges that are accessible only through private connections. When your server connects to 199.36.153.8, the traffic flows through your interconnect or VPN tunnel. Your cloud router then forwards this traffic to Google's private API endpoints, which serve the same APIs as the public endpoints but are only accessible via private connectivity. The APIs can't tell the difference. They respond normally. There are actually 2 private IP ranges available. 199.36.153.8/30 for standard private access, and 199.36.153.4/30 for restricted access that's compatible with VPC's service controls. The restricted range provides additional security controls for organizations with strict data governance requirements. The beauty of this solution is that it requires no changes to your applications. They continue to use the same API endpoints, but traffic flows privately. However, It does require careful coordination between your network team for DNS configuration and BGP route advertisement. DNS configuration for private access. DNS configuration is absolutely critical for private Google access to work correctly. You need to configure your corporate DNS servers to resolve Google API domains to private IP addresses instead of public ones. I am showing you two approaches here. Option A uses standard private access with the 199.36.153.8/30 range. This works for most use cases and provides access to the full range of Google APIs. The key configuration is creating a zone for googleapis.com and using a wildcard CNAME record that points all subdomains to private.googleapis.com. When Google's DNS resolves private.googleapis.com, it returns IP addresses in the 199.36.153.8/30 range. Option B shows the configuration for VPC service controls compatibility using the restricted.googleapis.com endpoint. This resolves to the 199.36.153.4/30 range and only works with APIs that support VPC service controls. Why use the restricted range? If your organization has implemented VPC service controls to prevent data exfiltration, you must use the restricted endpoint. The standard private endpoint bypasses VPC service controls, which could violate your security policies. The serial number in the SOA record should be updated whenever you make changes to ensure proper DNS propagation. The TTL values control how long DNS responses are cached. Shorter TTLs mean faster updates but more DNS queries. Remember that this DNS configuration must be coordinated across all your DNS servers and any DNS forwarders in your network. A single misconfigured DNS server can break API access for an entire subnet. BGP route advertisement setup. After configuring DNS, you need to ensure that traffic to the private Google API ranges actually flows through your private connection. This is where BGP route advertisement becomes crucial. The cloud router must advertise the private Google API ranges to your on-premises network so your routers know how to reach these destinations. Without these route advertisements, your on-premises routers will try to send this traffic to their default gateway, which likely leads to the public internet. For standard private access, you advertise 199.36.153.8/30. For VPC service controls compatibility, you advertise 199.36.153.4/30. Many organizations advertise both ranges to support different use cases or migration scenarios. The advertisement -mode equals CUSTOM parameter is important here because you're not just advertising your VPC subnets, you're also advertising these special Google-owned ranges. DEFAULT mode only advertises subnet routes. The set-advertisement-ranges parameter takes a comma-separated list of CIDR blocks. Each range you specify here will be advertised to your on-premises BGP peers. Your on-premises routers will learn these routes and install them in their routing tables. Always verify that the routes are being advertised correctly using the get-status command. The output shows you exactly which routes are being sent to your on-premises routers. If you don't see the private API ranges in this output, your on-premises servers won't be able to reach Google APIs privately. Remember that BGP route advertisement happens automatically once configured, but it can take a few minutes for routes to propagate through your network. Monitor your on-premises routing tables to confirm the routes are being received and installed correctly. Firewall configuration is often overlooked but absolutely critical for private Google access to work correctly. You need to allow traffic from your internal networks to the private Google API ranges on port 443. The firewall rules I'm showing here are examples for different firewall platforms. For Cisco ASA, you create access list entries that permit TCP traffic from your internal subnets, the 10.0.0.0 CIDR 8 range, to the private API ranges on port 443. For IP tables-based firewalls, you use output rules to allow outbound HTTPS traffic to the private ranges. Remember that Google APIs use HTTPS exclusively, so you only need to allow port 443. The testing phase is crucial and often reveals configuration issues. Start with DNS resolution. nslookup.storage.googleapis.com should return an IP address in the 199.36.153.x range, not a public IP address. The curl test with the -I flag performs a head request, which tests connectivity without downloading data. If this works, you know your firewall rules and routing are correct. Traceroute is particularly valuable because it shows you the path traffic takes to reach the API endpoint. You should see the traffic going through your private connection infrastructure, not out to the public internet. The G-Cloud storage test is the ultimate validation. If your G-Cloud CLI can list buckets from an on-premises server without public internet access, you know everything is working correctly. One common issue is DNS caching. If you recently changed your DNS configuration, you might need to flush DNS caches on client machines or wait for TTL expiration before tests work correctly. Private Service Connect Introduction. Private Service Connect represents a more modern and granular approach to accessing Google APIs privately. Instead of using shared IP ranges like private Google Access, PSC creates dedicated endpoints within your own VPC network. The key difference is control and visibility. With private Google Access, you're using Google-owned IP addresses that are shared across all customers. With PSC, you get dedicated IP addresses from your own VPC subnets that you can apply firewall rules to. Look at the architecture diagram. Instead of redirecting to shared 199.36.153.x addresses, your DNS points to dedicated IP addresses in your VPC, like 192.168.1.100. These are real IP addresses in your subnet that you fully control. PSC offers different service attachments for different use cases. The All APIs attachment provides access to the complete Google API suite. The VPCSC attachment only includes APIs that support VPC service controls, providing tighter security. You can even create endpoints for individual services like cloud storage. This granular control comes with benefits. For example, you can apply VPC firewall rules to control which on-premises networks can access which APIs. You get dedicated IP addresses for monitoring and logging, and DNS configuration is simpler with straightforward records. The trade-offs include per endpoint costs and regional scope. Each PSC endpoint has a monthly charge, and endpoints are regional resources, so you need separate endpoints in each region where you want private API access. For enterprises with strict security requirements or complex compliance needs, PSC often justifies its additional cost through the enhanced control and visibility it provides. Creating PSC endpoints. Creating Private Service Connect endpoints involves several coordinated steps. Let me walk you through each command and explain why each parameter matters for your overall architecture. First, we create a reserved IP address specifically for the PSC endpoint. The purpose parameter, set to Private Service Connect, tells Google Cloud this IP will be used for a PSC endpoint, not a regular virtual machine. The subnet parameter is crucial. This IP address comes from your existing VPC subnet, so it must be within the subnet's CIDR range and not already assigned to another resource. The forwarding rule is where the magic happens. The target service attachment parameter specifies which Google service you're connecting to. The path format is standardized. Project/service networking GCP/region/service attachments/service. For the All APIs attachment, you get access to most Google APIs through a single endpoint. This is cost-effective if you use multiple APIs and don't need granular access controls. The VPC-SC attachment is specifically for organizations using VPC service controls. Only APIs that support VPC-SC are available through this endpoint, but you get enhanced security controls and audit logging. Service-specific attachments like StorageGoogleAPIs.com provide access to individual APIs. This is ideal when you only use one or two APIs and want maximum security segmentation. The service directory registration parameter is optional but recommended. It automatically registers your endpoint with service directory for easier discovery and management. Always run the addresses list command after creation to verify your IP assignments. These IP addresses need to be documented and shared with your DNS team for the next configuration step. PSC DNS configuration. DNS configuration for Private Service Connect is actually simpler than private Google Access because you are using straightforward records pointing to your dedicated IP addresses instead of complex CNAME redirections. The beauty of PSC DNS configuration is its flexibility. You can point specific API services to specific endpoints, or point all APIs to a single endpoint depending on your architecture. In the first example, I am showing targeted configuration where storage.googleapis.com points to a dedicated storage endpoint at 192.168.1.102, while BigQuery.googleapis.com and PubSub.googleapis.com point to a shared all APIs endpoint at 192.168.1.100. The wildcard approach points all googleapis.com subdomains to a single endpoint. This is simpler to manage but gives you less granular control over which APIs different parts of your organization can access. For Windows environments, the PowerShell commands achieve the same result. The Add DNS Server Resource Record A commandlet creates a records in your DNS zones. Make sure you have the proper DNS administration privileges to make these changes. One key advantage of PSC DNS configuration is that changes are immediate and straightforward. You are not dealing with CNAME chains or complex DNS redirections. Just simple records that point to IP addresses you control. Remember to coordinate TTL values with your network team. Shorter TTLs allow faster changes but increase DNS query load. Longer TTLs reduce query load but slow down recovery if you need to change endpoint IP addresses. Always test DNS resolution from multiple points in your network to ensure consistent behavior. DNS configuration errors are among the most common causes of PSC connectivity issues. VPC firewall rules for PSC. One of the major advantages of Private Service Connect is the ability to apply VPC firewall rules to control access to Google APIs. This gives you granular security controls that are impossible with private Google access. The first rule I'm showing allows specific on-premises networks to access PSC endpoints. By specifying the source range as 10.0.0.0/8, you're limiting access to your corporate network while blocking any other potential sources. The target tags parameter could be used if you want to apply rules to specific endpoints, but since PSC endpoints don't actually have tags, it's more common to use destination ranges to target specific endpoint IP addresses. The second rule shows how you can get really granular. Maybe your database servers in the 10.1.100.0/24 subnet should be the only machines allowed to access BigQuery. You can enforce this at the network level with destination ranges pointing to your BigQuery PSC endpoint. The deny rule at the end provides defense in depth. By setting a lower priority, higher number, this rule blocks all other traffic to your PSC endpoints that doesn't match your specific allow rules. This prevents unauthorized access even if someone compromises your network. Priority matters enormously in VPC firewall rules. Lower numbers, higher priority, are evaluated first. So your specific allow rules might have priority 1000, while your general deny rule has priority 2000. Remember that VPC firewall rules are stateful for TCP and UDP traffic. If you allow outbound traffic to port 443, the return traffic is automatically allowed back. These firewall capabilities make PSC particularly valuable for enterprises with strict security requirements or complex compliance needs. You can implement network-level controls that complement your application-level authentication and authorization. PSC testing and verification. Testing and verification are critical for PSC deployments because there are many moving parts that must work together correctly. Let me walk you through a systematic testing approach that will catch most configuration issues. Start by verifying that your PSC endpoints are healthy using the forwarding rules list command. The status should show as healthy, and you should see your assigned IP's addresses. If an endpoint shows as unhealthy, there's likely an issue with the service attachment or network configuration. DNS testing comes next and is often where issues surface. The NSLOOKUP command should return your PSC endpoint IP address, not a public IP. If you're seeing public IPs, check your DNS configuration and DNS server selection. The curl test with -I flag performs a HEAD request to test connectivity without transferring data. This is perfect for testing because it's quick and doesn't consume a PI's quotas. Success here means your firewall rules, routing, and endpoint configuration are correct. Testing with the G-Cloud CLI using the verbosity equals debug flag provides detailed logging that shows you exactly which IP address the client is connecting to. This is invaluable for troubleshooting because it shows the complete connection process. The router status check is important because PSC endpoints automatically create routes in your VPC. The get status command shows you these automatically advertised routes. Your on-premises routers should be learning these routes through BGP. Unlike private Google access, PSC endpoints automatically advertise their routes to on-premises networks. You don't need to configure custom route advertisement. Google Cloud handles this automatically when you create the endpoints. If tests fail, work systematically through the layers. DNS resolution first, then routing, then firewall rules, then endpoint health. Most PSC issues are DNS or firewall related rather than fundamental connectivity problems. Remember that PSC endpoints can take a few minutes to become fully operational after creation. If immediate tests fail, wait 5 to 10 minutes and try again before troubleshooting other components. Multi-region hybrid architecture. Real enterprise deployments often require connectivity from multiple on-premises locations to multiple Google Cloud regions. This creates complex routing scenarios that require careful planning and design. The architecture shown demonstrates a common pattern where you have two data centers, one on the East Coast and one on the West Coast, each needing connectivity to different Google Cloud regions for latency optimization and disaster recovery. Notice how the connectivity types can be mixed. Your primary East Coast data center might use Cloud Interconnect for high bandwidth and consistent performance, while your West Coast location uses HAVPN for cost efficiency and faster deployment. The MPLS network in the middle is crucial for many enterprises. It provides any-to-any connectivity between your sites, which means traffic from any data center can reach any Google Cloud region through the optimal path. VPC peering between the Google Cloud regions enables resources in one region to communicate with resources in another. This is essential for applications that span multiple regions or for disaster recovery scenarios. Each cloud router is regional and manages BGP sessions for its specific region. However, with global dynamic routing enabled, each router can learn and advertise routes for subnets in all regions of the VPC, not just its local region. This architecture provides redundancy at multiple levels. If one data center fails, traffic can flow through the other. If one Google Cloud region has issues, workloads can fail over to another region. The MPLS network provides multiple paths between sites. Wrench hybrid DNS resolution setup. DNS in hybrid environments can become complex because you need seamless resolution between on-premises and cloud resources. Cloud DNS provides powerful features for hybrid scenarios through private zones and DNS forwarding. The first command creates a private DNS zone for your on-premises domain. This allows Google Cloud resources to resolve names of on-premises servers, databases, and services. The networks parameter restricts this zone to your specific VPC. When you add a records to this zone, you are essentially teaching Google Cloud virtual machines how to reach your on-premises services. For example, mail.corp.example.com might point to your on-premises Exchange server. The forwarding zone is even more powerful. Instead of manually adding records for every on-premises service, you can forward entire domains to your on-premises DNS servers. This means Google Cloud virtual machines will automatically resolve any name in the internal .corp.com domain by asking your DNS servers. The forwarding -targets parameter should list your on-premises DNS server IP addresses. These must be reachable through your VPN or interconnect connection. Always specify multiple DNS servers for redundancy. The DNS policy ties everything together. Enable -inbound -forwarding allows your on-premises servers to query Cloud DNS for Google Cloud resource names. Enable -logging provides detailed DNS query logs for troubleshooting and security monitoring. This bidirectional DNS resolution is critical for hybrid applications where cloud services need to call on-premises APIs and vice versa. Without proper DNS, applications resort to hard-coded IP addresses, which are fragile and difficult to maintain. Shared VPC for centralized connectivity. Shared VPC is a game-changer for enterprises because it allows you to centralize network connectivity while maintaining project isolation. This is especially powerful for hybrid architectures where you want a single point of connectivity management. The host project owns all networking resources, VPCs, subnets, cloud routers, VPN gateways, and interconnect attachments. This centralizes hybrid connectivity under a single administrative domain, typically managed by your network operations team. Service projects can use the shared network resources but cannot modify them. This provides the perfect separation of concerns. Application teams get network connectivity without having to understand the complexities of hybrid networking. The IAM configuration is crucial here. The compute network user role allows service project users to create resources that use the shared network, but they cannot modify firewall rules or routing configuration. Notice how the subnet creation includes secondary ranges for GKE pods and services. This is a common pattern where the network team pre-provisions subnets with the appropriate IP ranges for different use cases. Different service projects can have subnets in different regions or even overlapping IP ranges in different VPCs, all while sharing the same hybrid connectivity infrastructure. This model scales beautifully. You can have hundreds of service projects all sharing the same VPN or interconnect connections, with centralized billing, monitoring, and management of the network infrastructure. Security is enhanced because network policies are enforced at the host project level, preventing individual application teams from accidentally creating security holes in your hybrid connectivity. Network security controls. Network security in hybrid environments requires layered controls that protect both the connectivity infrastructure and the applications using it. Google Cloud provides several powerful tools for implementing these controls. Hierarchical firewall policies operate above individual VPC firewall rules, providing organization-wide security controls. The policy I'm showing applies to all VPCs in your organization, ensuring consistent security across all projects. The first rule allows essential management traffic from your on-premises networks. Notice how we're allowing SSH, HTTPS, and RDP. These are typically needed for system administration and monitoring. The rule applies to all resources receiving traffic from your corporate IP ranges. The deny rule is equally important. It blocks all internet access from your hybrid subnet ranges. This enforces the principle that hybrid workloads should not have direct internet access, which is a common enterprise security requirement. The association command applies the policy to specific VPC networks. You can apply the same policy to multiple VPCs, ensuring consistent security controls across your hybrid infrastructure. Cloud Armor provides additional protection for workloads exposed through load balancers. The security policy here only allows traffic from your on-premises IP ranges, blocking all other internet traffic. This layered approach means that even if someone compromises a virtual machine in your hybrid environment, they cannot access the broader internet or reach other networks outside your approved IP ranges. The beauty of hierarchical policies is that they cannot be overridden by project-level rules, ensuring that critical security controls cannot be accidentally disabled by application teams. BGP Session Troubleshooting. BGP troubleshooting is critical because BGP failures are often the root cause of hybrid connectivity issues. When BGP sessions are down, you have connectivity at the physical layer but no traffic flow. The Get Status command is your first diagnostic tool. It shows you the state of each BGP peer. Established means working. Anything else indicates a problem. The num learned routes tells you how many routes your cloud router has learned from the on-premises side. Zero learned routes often indicates a configuration mismatch. Check that your on-premises router is advertising routes and that the ASN numbers match between the BGP peer configuration and your actual router. The detailed YAML output shows BGP attributes, timers, and error counters. Look for authentication failures, which usually indicate mismatched shared secrets or IP addresses. Advertised routes show what Google Cloud is telling your on-premises network. If you don't see your VPC's subnet ranges here, check your advertisement mode and custom route configuration. Learned routes show what your on-premises router is advertising to Google Cloud. Missing routes here indicate on-premises BGP configuration issues. BGP session flapping, rapid up or down transitions, often indicates network instability, MTU mismatches, or router resource constraints. Check for packet loss or latency spikes in your connectivity layer. Remember that BGP convergence takes time. After making configuration changes, wait 5 to 10 minutes before concluding that something is broken. BGP is designed for stability, not speed. VPN tunnel troubleshooting. VPN troubleshooting requires understanding the layered nature of IPsec connections. You need the physical internet connection, the IPsec tunnel established, and the BGP session established. All of these must be working together. The tunnel status command shows the overall health of each tunnel. Established means the IPsec tunnel is up, but that doesn't guarantee traffic flow. You also need the BGP session over that tunnel to be working. The detailed tunnel description shows traffic selectors, which define what traffic can flow through the tunnel. Mismatched traffic selectors are a common cause of connectivity issues. Check the external IP addresses assigned to your AHVPN gateway. These are the IPs your on-premises VPN devices must connect to. If these IPs change, which is rare but possible, you need to update your on-premises configuration. VPN metrics in cloud logging reveal detailed tunnel establishment events, authentication failures, and tunnel teardowns. Look for repeated authentication failures, which indicate shared secret mismatches. IKE, Internet Key Exchange, errors are particularly important. IKE Phase 1 failures indicate authentication or proposal mismatches. IKE Phase 2 failures indicate traffic selector or security association problems. Tunnel flapping often indicates MTU issues. VPN adds overhead to packets, so if your on-premises MTU is too large, packets get fragmented or dropped. Standard VPN MTU is 1460 bytes. Always test with ping first, then traceroute to verify the path. If ping works but applications don't, check for firewall rules blocking specific ports or protocols. Private Google Access Troubleshooting. Private Google Access troubleshooting often involves DNS resolution issues and routing problems. Since this feature relies on DNS redirection and BGP route advertisement, both must work correctly. Start with DNS testing from your on-premises servers. The NSLOOKUP command should return IP addresses in the 199.36.153.x range, not public IP addresses. If you're getting public IPs, check your DNS server configuration and DNS search order. The dig command provides more detailed DNS debugging information, including which DNS server provided the response and the complete query path. curl with verbose output shows the complete HTTP handshake, including which IP address the client connects to. This is crucial for verifying that traffic is actually using the private path. Test specific API endpoints because some Google services have different DNS names or routing requirements. Don't assume that if one API works, all APIs will work. The routing table checks are critical. Your on-premises routers must have routes to the 199.36.153.x ranges pointing toward your Google Cloud connection. Use your router's route lookup commands to verify. VPC firewall rules don't apply to private Google access traffic because the destination IPs are Google-owned, not in your VPC. However, your on-premises firewall rules still apply. A common mistake is not coordinating DNS changes across all DNS servers in your network. One misconfigured DNS server can break API access for an entire subnet. Remember that DNS caching can mask configuration changes. After making DNS changes, flush DNS caches on client machines or wait for TTL expiration before concluding that changes aren't working. Troubleshooting Private Service Connect, or PSC, is generally easier than private Google access. This is because you are dealing with dedicated IP addresses in your own VPC. However, the additional complexity of forwarding rules and service attachments creates new failure points. Always start by checking PSC endpoint health. Unhealthy endpoints indicate problems with the service attachment or network configuration. The target field shows which Google service attachment you are connecting to. DNS resolution for PSC should return your dedicated VPC IP addresses. If you are getting public IPs, check your DNS configuration. If you are getting no response, check your DNS server connectivity. The curl test verifies end-to-end connectivity. Success here means your DNS, routing, firewall rules, and PSC endpoint are all working correctly. Using G-Cloud with debug verbosity shows exactly which IP address the client connects to, and any authentication or authorization errors. This is invaluable for troubleshooting API access issues. PSC endpoints automatically create routes in your VPC and advertise them to on-premises networks. The router status check verifies these routes are being advertised correctly via BGP. Unlike private Google access, PSC endpoints support VPC firewall rules. Check both your allow rules, used to permit access, and any deny rules that might be blocking traffic. PSC endpoints can take several minutes to become fully operational after creation. If immediate tests fail, wait 5 to 10 minutes before troubleshooting other components. Service attachment compatibility is important. Make sure you are using the correct attachment for your use case. The VPC-SC attachment only works with VPC service controls compatible APIs. Monitoring and observability setup. Comprehensive monitoring is essential for hybrid connectivity because failures can occur at multiple layers: physical connectivity, routing protocols, DNS resolution, and application-level access. Uptime checks provide synthetic monitoring that continuously tests your hybrid connectivity from Google's monitoring infrastructure. The check I'm showing tests API connectivity, which validates the entire stack from DNS resolution to API response. The HTTP check parameters are important. Use port 443 for HTTPS, set reasonable timeouts, and test frequently enough to catch issues quickly but not so frequently that you overwhelm your systems. Alerting policies should trigger when connectivity fails, but also when performance degrades. Create policies for BGP session failures, VPN tunnel failures, and DNS resolution failures. The VPN tunnel alert policy monitors tunnel state and triggers when tunnels go down. This is critical because with HAVPN, you might not notice a single tunnel failure, but it reduces your redundancy. BGP session health monitoring catches routing issues before they become connectivity failures. Monitor for session state changes and route count variations. Custom metrics let you track hybrid-specific events like traffic volume over your connections, API's call success rates, and DNS resolution performance. Logging is crucial for post-incident analysis. Enable VPC flow logs to track traffic patterns, DNS query logs to debug resolution issues, and BGP logs to understand routing changes. Set up dashboards that show the health of your entire hybrid infrastructure at a glance. Include metrics for connectivity utilization, error rates, and latency from both Google Cloud and on-premises perspective. Performance optimization in hybrid environments involves tuning multiple layers, from BGP convergence times to application-level optimizations. The goal is to minimize latency and maximize throughput while maintaining reliability. BGP advertisement intervals control how quickly routing changes propagate. Faster intervals mean quicker failover but more BGP update traffic. The custom advertisement ranges ensure you are only advertising the routes you actually need. Advertised route priority becomes important when you have multiple paths to the same destination. Higher priority routes, lower numbers, are preferred by BGP, allowing you to control traffic flows. ECMP, equal cost multipath, routing distributes traffic across multiple VPN tunnels or interconnect connections. This requires identical BGP metrics across all paths and compatible router configurations. MTU optimization is critical for VPN connections. The standard 1460-byte MTU accounts for IPsec overhead while avoiding fragmentation. Test with ping using the Do Not Fragment flag to verify optimal MTU settings. TCP MSS clamping on your routers can help with MTU discovery issues. Set MSS to 1420 bytes for VPN tunnels to prevent TCP session problems. Consider traffic shaping and QoS policies to prioritize critical applications over your hybrid connections. Database replication and real-time applications should get priority over batch transfers. Regional placement of cloud routers affects latency. Place routers in regions close to your on-premises locations and your primary workloads. Monitor bandwidth utilization and plan for growth. Interconnect connections can be upgraded, but VPN connections have hard bandwidth limits that require additional tunnels to exceed. Application-level optimizations like connection pooling, caching, and compression often provide more performance improvement than network-level tuning, especially for API-heavy workloads. Advanced troubleshooting scenarios. In real-world deployments, you'll encounter complex troubleshooting scenarios that require systematic approaches and a deep understanding of multiple interconnected systems. Let me walk you through some of the most challenging scenarios I've seen in enterprise environments. Intermittent connectivity issues are particularly frustrating because they are hard to reproduce and diagnose. These often stem from BGP flapping, where sessions rapidly go up and down due to network instability, timer mismatches, or resource constraints on routers. Asymmetric routing is a subtle but critical issue where traffic flows differently in each direction. This can happen when you have multiple connectivity paths with different BGP metrics. Traffic might go out via interconnect but return via VPN, causing performance issues or connection failures. DNS split-brain scenarios occur when on-premises and cloud DNS servers have conflicting information about the same domain. This creates situations where some clients resolve names one way while others resolve them differently, leading to seemingly random connectivity failures. MTU black hole problems are especially tricky with VPN connections. Large packets get silently dropped because ICMP responses are blocked, making applications hang without obvious error messages. This requires systematic MTU discovery and path testing. The troubleshooting methodology I am showing follows the OSI model from bottom to top. Physical connectivity first, then data link, network, transport, and finally application layers. Each layer has specific diagnostic tools and approaches. Always document your troubleshooting steps and findings. Complex hybrid issues often require multiple team members and vendor support, so having a clear timeline of what was tested and when is invaluable. Cost optimization strategies. Cost optimization in hybrid connectivity requires understanding both the direct costs of connections and the indirect costs of data transfer, latency-sensitive applications, and operational overhead. The interconnect versus VPN cost analysis isn't just about connection fees. You need to factor in data transfer costs, which can be substantial for high-volume workloads. Interconnect typically has lower data transfer costs than VPN, which goes over public internet. Regional placement decisions have major cost implications. Placing workloads in regions close to your interconnect locations reduces latency and often reduces data transfer costs. But this needs to be balanced against regional pricing differences for compute and storage. Committed use discounts for bandwidth can provide significant savings if you can predict your usage patterns. But be careful. These commitments can lock you in for 1 to 3 years, so ensure your architecture is stable before committing. Partner interconnect often provides better cost-performance ratios for medium-scale deployments. You get dedicated connectivity benefits without the minimum bandwidth commitments and setup costs of dedicated interconnect. PSC endpoint costs need to be carefully managed because you pay per endpoint per month. Consider consolidating APIs through all APIs endpoints rather than creating separate endpoints for each service unless you need granular access controls. Traffic engineering can reduce costs by routing non-critical traffic through lower-cost paths. Use BGP communities and route preferences to send backup traffic through VPN while keeping primary traffic on interconnect. Monitor your actual usage patterns monthly. Many organizations over-provision connectivity based on peak theoretical usage rather than actual traffic patterns. Right-sizing connections can provide substantial savings. Security deep dive topics. Security in hybrid environments involves multiple layers and requires coordination between your on-premises security teams and cloud security controls. The shared responsibility model becomes complex when you're bridging two environments. VPC service controls create security perimeters around your Google Cloud resources, preventing data exfiltration even if credentials are compromised. When combined with private Google access using the restricted endpoint, you get comprehensive data protection. The integration with IAP is powerful for hybrid applications. IAP can protect applications running in Google Cloud while authenticating against your on-premises Active Directory through Cloud Identity Federation. Network segmentation becomes critical in hybrid environments. Use VPC firewall rules, hierarchical policies, and CloudNet to ensure that compromised on-premises systems cannot access your entire cloud infrastructure. Certificate management requires careful planning. Consider using Google's Certificate Authority service for internal certificates that work across both environments, or ensure your existing PKI infrastructure can issue certificates for cloud resources. Audit logging must cover both environments to provide complete visibility. Enable VPC flow logs, DNS query logs, and Google Cloud Audit logs, then correlate them with your on-premises security monitoring systems. Zero Trust networking principles apply strongly to hybrid environments. Never assume that traffic from on-premises networks is trusted. Implement authentication and authorization at every layer. Incident response procedures need to account for hybrid scenarios. Your security team needs runbooks for isolating compromised cloud resources while maintaining business continuity for critical hybrid applications. Disaster recovery patterns. Disaster recovery in hybrid environments is complex because you need to protect against failures in both your on-premises infrastructure and your cloud connectivity. The goal is to maintain business continuity regardless of where failures occur. The multi-path connectivity shown in the diagram is essential for DR. Notice how we have multiple connectivity types to multiple regions. If your primary interconnect fails, traffic can failover to VPN. If your primary region fails, workloads can failover to a secondary region. Database replication across the hybrid boundary is often the most critical component. Whether you're using Cloud SQL cross-region replicas, or replicating from on-premises databases to cloud databases, the replication must work over your private connectivity. DNS failover mechanisms need to be automated and tested regularly. Use Cloud DNS with health checks to automatically redirect traffic from failed on-premises services to cloud replicas, or vice versa. Application-level failover is often more reliable than network-level failover. Design applications to detect connectivity failures and switch data sources or API endpoints automatically. Storage replication strategies vary by workload. For file shares, consider Cloud File Store with cross-region replication. For object storage, use Cloud Storage multi-region buckets or cross-region replication. Recovery Time Objective, RTO, and Recovery Point Objective, RPO, requirements drive your architecture decisions. Sub-minute RTOs require active-active configurations with automatic failover. Longer RTOs allow for manual failover procedures. Test your DR procedures regularly under realistic conditions. Many DR plans look good on paper but fail during actual outages due to untested dependencies or configuration drift. Consider cascading failure scenarios. What happens if your on-premises data center fails at the same time as your primary cloud region? Design for multiple simultaneous failures in truly critical systems. Migration strategies. Migrating to hybrid connectivity requires careful planning and phased execution. Most enterprises cannot simply flip a switch and move from on-premises to hybrid. It requires months of planning and gradual transition. The assessment phase is critical and often underestimated. You need to catalog all applications, their dependencies, network requirements, and integration points. Use tools like Migrate for Compute Engine's Discovery Agent to automate this inventory. Pilot deployment should focus on non-critical applications first. Choose applications with minimal dependencies and well-understood network requirements. This validates your connectivity design before migrating business-critical systems. Gradual migration allows you to move applications in waves while maintaining business continuity. Each wave should include related applications to minimize cross-wave dependencies. Plan for rollback procedures in case issues arise. Optimization happens after migration when you have real usage data. Monitor application performance, network utilization, and user experience to identify optimization opportunities. The database migration strategy often determines the overall timeline. Consider using Database Migration Service for managed migrations, or implement change data capture for real-time synchronization during transition periods. Network dependency mapping is crucial for planning migration waves. Applications that communicate frequently should be migrated together to minimize latency and bandwidth consumption over hybrid connections. Staff training and change management are often overlooked but critical for success. Your operations teams need to understand hybrid troubleshooting. Your security teams need to understand new threat models, and your developers need to understand hybrid application patterns. Cost tracking during migration helps validate business cases and identify unexpected expenses. Track not just cloud costs but also increased networking costs, training costs, and temporary operational overhead. Best practices and governance. Establishing governance frameworks for hybrid connectivity is essential for maintaining security, performance, and cost control as your hybrid environment grows. Without proper governance, hybrid environments can become an unmanageable sprawl. Network design standards should specify IP addressing schemes, subnet sizing, firewall rule patterns, and naming conventions. These standards prevent conflicts and make troubleshooting much easier when you have hundreds of resources. Change management processes become critical because changes in one environment can affect the other. Implement approval workflows for firewall changes, routing changes, and DNS modifications that could impact hybrid connectivity. Monitoring and alerting standards ensure consistent visibility across your hybrid infrastructure. Define standard metrics, alerting thresholds, and escalation procedures that work across both environments. Security policies must address the expanded attack surface of hybrid environments. This includes network segmentation policies, access control standards, and incident response procedures that work across environments. Cost governance prevents runaway expenses from unmanaged resource growth. Implement budget alerts, resource tagging standards, and regular cost reviews. Consider using cloud asset inventory to track resource creation and modifications. Documentation standards are crucial for hybrid environments because the complexity makes tribal knowledge dangerous. Maintain current network diagrams, runbooks, and configuration documentation. Regular audits help maintain compliance with governance policies. Use tools like Cloud Security Command Center and Cloud Asset Inventory to identify configuration drift and policy violations. Training programs ensure your teams can effectively manage the hybrid environment. This includes technical training on Google Cloud networking, but also process training on governance procedures and escalation paths. Real-world case studies. Let me share some real-world scenarios that illustrate common challenges and solutions in hybrid connectivity deployments. These examples are based on actual customer implementations I have worked with. The financial services case demonstrates the importance of compliance and security in hybrid deployments. This customer needed to maintain PCI DSS compliance while moving payment processing to the cloud. They used VPC service controls with restricted private Google access to ensure that payment data never traversed public networks. The key insight from this case was that compliance requirements drove architecture decisions. They needed audit logs showing that all payment data stayed within their controlled network perimeter, which required careful design of both connectivity and monitoring. The manufacturing company case shows how hybrid connectivity enables digital transformation while preserving existing investments. They had millions of dollars invested in on-premises ERP systems that could not be easily migrated. Their solution used Private Service Connect to allow on-premises applications to access BigQuery for analytics while keeping transactional data on-premises. This hybrid architecture enabled advanced analytics without requiring a complete ERP replacement. The retail chain case illustrates the challenges of multi-location connectivity. With hundreds of stores, they needed cost-effective connectivity that could scale. They used a hub-and-spoke model with partner interconnect at regional distribution centers. The clever part of their solution was using Cloud NAT at store locations for internet traffic while routing internal traffic through the regional hubs. This reduced connectivity costs while maintaining security. Each case study highlights the importance of understanding business requirements first, then designing technical solutions to meet those requirements. Technology decisions should always be driven by business outcomes, not technical preferences. The hybrid connectivity landscape continues to evolve rapidly, and understanding future trends helps you make architecture decisions that will remain relevant as technology advances. Software-defined networking is increasingly important in hybrid environments. Google Cloud's network virtualization technologies like Anthos Service Mesh provide consistent networking abstractions across on-premises and cloud environments. Edge computing integration is becoming critical for latency-sensitive applications. Google's distributed cloud offerings allow you to run Google Cloud services at edge locations, connected via your hybrid network infrastructure. AI and machine learning are being integrated into network operations. Expect to see more automated troubleshooting, predictive capacity planning, and intelligent traffic routing based on application requirements. Zero-trust networking principles are becoming the default for enterprise security. This means moving away from network perimeter security toward application-level security with continuous verification. Multi-cloud connectivity is increasingly common as enterprises adopt best-of-breed cloud services. Your hybrid connectivity strategy should consider how to integrate not just Google Cloud but also AWS, Azure, and other cloud providers. Sustainability concerns are influencing connectivity decisions. Consider the carbon footprint of your network architecture, especially for high-bandwidth applications. Shorter network paths and more efficient routing can reduce environmental impact. Automation and infrastructure as code become essential as hybrid environments grow in complexity. Tools like Terraform, Cloud Deployment Manager, and Config Connector help maintain consistency and reduce manual errors. Plan for these trends by designing flexible architectures that can adapt to new technologies without requiring complete rebuilds. This typically means favoring software-defined solutions over hardware-dependent implementations where possible. If you're preparing for the Google Cloud Network Specialty Certification, hybrid connectivity topics are heavily weighted and require deep understanding, not just memorization. Let me share the most important areas to focus on. The IP address ranges are absolutely critical to memorize. 199.36.153.8/30 for private Google access, and 199.36.153.4/30 for restricted access. You'll see questions that require you to identify which range to use in different scenarios. BGP concepts appear frequently, especially ASN assignment, route advertisement, and troubleshooting scenarios. Understand how BGP metrics affect path selection and how to configure route preferences for traffic engineering. Understand the differences between private Google Access and Private Service Connect in detail. Know when to use each approach, their cost implications, and their security characteristics. Questions often present scenarios where you need to choose the appropriate solution. HAVPN configuration details are tested extensively. Memorize the 4-tunnel configuration pattern. Understand why it provides 99.99% SLA, and know how to troubleshoot common VPN issues like authentication failures and MTU problems. Interconnect concepts include the differences between dedicated and partner interconnect, VLAN attachment configuration, and the letter of authorization process. Questions often test your understanding of when to recommend each type. Shared VPC scenarios test your understanding of IAM roles, cross-project networking, and centralized network management. Know the roles like compute.network user, and understand host project versus service project responsibilities. DNS integration scenarios are common, including cloud DNS forwarding zones, inbound forwarding, and hybrid name resolution. Understand how to design DNS architectures that work bi-directionally. Practice with hands-on labs whenever possible. The exam includes scenario-based questions that require understanding how all the pieces work together, not just individual component knowledge. We've covered the complete spectrum of Google Cloud hybrid connectivity, from basic concepts to advanced enterprise patterns. Let me summarize the key decisions you need to make and the steps to move forward. Your connectivity foundation choice between VPN and interconnect depends primarily on bandwidth requirements, budget, and timeline. VPN provides quick deployment and lower initial costs, while interconnect provides better performance and lower long-term costs for high bandwidth scenarios. For private API access, choose private Google Access for simplicity and cost-effectiveness, or Private Service Connect when you need granular firewall controls and dedicated IPs. Most enterprises eventually migrate from PGA to PSC as their security requirements mature. The implementation roadmap should start with connectivity establishment, followed by DNS integration, then private API access configuration. Test thoroughly at each phase before proceeding to the next. Ongoing management requires monitoring, alerting, cost optimization, and regular review of security policies. Hybrid environments are living systems that require continuous attention to maintain optimal performance and security. Success metrics should include connectivity uptime, application performance, cost versus budget, and security incident reduction. Establish baseline measurements before implementation so you can demonstrate improvement. Next steps for your organization depend on your current state. If you're just starting, begin with the assessment and planning phase. If you have basic connectivity, Focus on optimizing performance and implementing advanced patterns like PSC. Remember that hybrid connectivity is not a destination but a journey. Technology continues to evolve, business requirements change, and you need to continuously adapt your architecture to meet new challenges. The investment in hybrid connectivity pays dividends in improved security, better performance, and reduced operational complexity. But success requires commitment to proper design, implementation, and ongoing management.